Let's go back to our man Wason, who gave us the 2, 4, 6 task. He had another experiment, this time in the realm of deductive reasoning. And we're going to have a look at the game he was playing with his subjects. Again, this is something that's fun to do in class, but hopefully you'll be able to play along at home, as it were. You see before you 4 cards, and you should understand that each card has a letter on one side and a number on the other. We know that in advance. Supposing I give you the following rule. If there is a vowel on one side, then there is an odd number on the other. Which cards do you have to turn over in order to test that rule? Pause the video now and make your choices. Which of these cards must you turn over to test the rule? And when you come back, I'll give you the answer. Okay, I assume you're back. If there's a vowel on one side, then there's an odd number on the others. Well, that looks like the first proposition, if A, then B, doesn't it? And we've got 4 consequences, 4 second propositions we can put there. We could assert vowel, that's A, and therefore we could conclude B. We could say there's not an odd number, not B, and therefore we could conclude there's not a vowel. The logical fallacies would suggest that if there's an odd number, that has consequences for whether there's a vowel or not. And the other logical fallacy would say if it's not a vowel, that we can draw inferences about the other side. Well, about 5 to 10% of university students get this correct on the first time. This seems to be Mr. Wason's game. He likes to critique university students' reasoning. So, letter A, let's see. Well, that looks like our modus ponens. If P then Q, so if there's a vowel, then there's an odd number, and here we see there's a vowel. So the rule requires there to be an odd number on the other side, so we're going to have to check that card. Now, the 4 corresponds to modus tollens. So we have if there's a vowel, then there's an odd number. And here we see there's not an odd number, so therefore there should not be a vowel on the other side. The rule does make a claim about what's on the other side of the card 4. It should not be a vowel. So A corresponds to modus ponens and 4 corresponds to modus tollens. The 7 corresponds to affirmation of the consequent. So if there's a vowel, then there's an odd number, and here there's an odd number. But that doesn't tell us anything about what's on the other side of the card. Affirmation of the consequent would deduce something wrongly. And for the same reason, D corresponds to denial of the antecedent. And I'm going to leave that one as an exercise to you. So did you get it right? Did you say A and 4, but not D and 7? It's quite difficult, isn't it? And the whole puzzle was presented in rather abstract terms. I don't suspect that you really care about odd numbers and vowels that much. I could be wrong. So is this a way to test people's reasoning abilities? Well, it turns out that if you make tasks relevant to people, they do much better. So supposing we had a rule, if you're under 18, you can't drink in pubs. That is alcoholic drinks. You're familiar with the rule. And supposing I gave you the job of being an inspector, so you're testing the rule, and you go in and you find these 4 cases in a pub. Someone's drinking a Coke, someone's drinking a beer, someone's 16 years old, and someone's 20 years old. Now, you can work through these again. They correspond exactly to the same 4 cases, not necessarily in the same order. Figure it out for yourself. But I don't think anyone would have any difficulty. If someone's drinking a Coke, who cares? If someone's drinking a beer, they better be of age. If someone's 16-year-old, you better check what they're drinking. If someone's 20 years old, who cares what they're drinking? I don't think any of you will get anything wrong on this. It says here 60 to 70% of people make the correct selections when you get this kind of semantic information compared to 5 to 10%. I suspect it's closer. If we set this up right, it will be closer to 100% of you would get it correct. So here we can see we've got a paradigm that allows us to do experiments to say something about, well, about what? Is it really testing our ability to think deductively? Or is it testing our ability to think deductively in an abstract, semantically vacuous sense when there's no field of meaning associated with it? I don't know. So we looked at just these four examples of frames: if P then Q, followed by a second assertion and then a conclusion. Propositional logic goes much further. We can enlarge the set of the kinds of propositions we have. So introducing the words all or some or no into our set gives us much more complicated syllogisms. So for example, taking an example from The Simpsons, if we have a proposition all Frenchmen are cheese eaters, and we have a proposition all cheese eaters are surrender monkeys, are we valid in deducing that all Frenchmen are surrender monkeys? And again, I'll point you to the fact we're not actually arguing about the truth or falseness of anything to do with Frenchmen. What we're looking at is, if you accept those first two propositions, does the third one follow? In fact, the third one does follow. It is logically valid, even though the whole argument is specious. Now, once we introduce all and some and no, along with not, the set of possible combinations becomes much larger. Instead of 4 alternatives, we now have 512 alternatives. And some of them will be valid forms of reasoning and some of them will be invalid forms of reasoning. So, can you imagine how many errors now can creep into these kinds of things? So, here's an example of a fallacy within this framework. All Frenchmen are cheese eaters, some cheese eaters are farmers, therefore some Frenchmen are farmers. Now, follow that through yourself. Think, does the third statement follow from the first? If you accept the first two, does the third one follow? In fact, it's a fallacy, one of very many fallacies lurking in these patterns. Some people like to explain people's performance on these in terms of belief. I don't know if that's the right way to do it. I do know that it's useful to be able to recognize valid and invalid chains of inference. I do know that the application of logic to real life situations is much harder than you might think. And I do know that these forms of deduction appear again and again, and it's very useful to be able to spot a bad one. So I'm going to finish up this unit with a poem, an excerpt from a poem. Go look up the whole one yourself. It's by a guy called Andrew Marvell. It's from 1681, and the poem is called To His Coy Mistress. And he's trying to seduce a woman. He's trying to argue with her in order to get her into his bed. So follow the argument here. Had we but world enough and time, this coyness lady were no crime. And then later. But at my back I always hear time's winged chariot hurrying near, and yonder all before us lie deserts of vast eternity. Then he reaches his conclusion. Now therefore, while the youthful hue sits on thy skin like morning dew, and while thy willing soul transpires at every pore with instant fires, now let us sport us while we may. Which of the four patterns we studied in detail does this one correspond to? Let's see. Had we but world enough and time, then go ahead and be coy. So if we've got all the time in the world, then don't bother about it. Second one, but we don't have all the time in the world. Not Q. Therefore not P. No, sorry, not P, therefore not Q. Even I can get it wrong. Follow it through and see if you can map this onto denial of the antecedent. And that's a satisfying place to end this.